If you want to gain more confidence in talking about AI neural networks but have no time, this is for you. In less than 40 minutes, we will go under the hood and take a whirlwind tour on key concepts such as model training, inference, cost functions, model losses, parameters and weights, gradient descent, perceptrons, nonlinearity, and network architectures. While you won't turn into a machine learning engineer overnight, you will develop a much stronger intuition and be more credible when talking about it at work. Don't be put off by the complicated looking math. It will all be explained assuming that you remember nothing from high school. This video is divided into 3 sections. The first one uses the simplest of examples from high school math to introduce key machine learning concepts. The second one explains gradient descent, and the last one introduces perceptrons, a key building block of modern-day neural networks, and how these can be pieced together to fit much more complicated real-world datasets. So here we go. In section 1, we're going to be taking you back to high school math and reminding you of what linear regression is. It might seem very simple and at this stage unclear how it's related to state-of-the-art artificial intelligence, but trust me, just in the next few minutes, you're going to learn some really key concepts that you will use over and over again when you work with AI systems. We're going to be covering concepts including what exactly we mean when we say model, the model weights or parameters, the losses of a model or the cost function, and the process of optimizing the parameters or weights such that we minimize the losses, aka model training. So let's jump straight into it. Imagine you have a data set that looks like this. Each dot represents a data point. And for each data point, given some value of x, there's a corresponding value of y. And what you would like to do is to fit a model to this data set such that you can use the model to predict values of y if someone gives you an x. So for example, if someone comes along and says 3, you want to be able to say, well, based on my model, maybe y is going to be something around 2.3. So just by eyeballing this very simple data set, we might say that kind of model that might fit this kind of data would be a straight line. If we take ourselves back to high school math, the equation for a line looks something like this. Y equals w times x plus b. So by changing these yellow parameters, or they're sometimes called weights, we can create a line that can best fit this data set, and then that would be our model. So this w is essentially the slope of the line. If we just remind ourselves of what exactly that means, w is the change in y divided by the change in x, and it would be some value, and what we want to do is to set w to the best value that it can be to fit this data set. And as you can see here, this line right now is quite far away from some of the data points because we've just randomly set some value for w and we have not optimized it. Likewise, the other parameter is called the intercept, b, and that is where the line hits the y-axis. By adjusting what w should be and adjusting what b should be, you should be able to fit a line that can represent this data set pretty well. Now, as I mentioned before, we just slapped this yellow line randomly on the chart. So in some places, it's quite far away from the real set of dots that we have. If we just used this yellow line as our model, the errors are going to be quite high. If we just take 3, for example, if someone came along and said, I have an x of 3, help me predict a value for y. And if we use this yellow line as our model, we go up and come along, y is 1.5, but actually, if we look at our real data, we have one that's pretty close, where x is pretty close to 3, and the y is actually up here at 2.5. So this red line, where our estimated y is, and where the real y should be, is called the error. And sometimes we like to have some kind of equation that can help us calculate how wrong our model is from the set of real data that we have. And we call this the cost function. And this looks a little bit complicated, but don't worry about it. It's actually very intuitive. What we're doing is just taking the length of all of these lines and squaring it. So when we square it, we actually take the negatives out of the calculation. We're just, any length of the line, as long as it's far away from the real data, is an error. So we square it, and then we add it all up, and then we divide it by the number of points, just so that we kind of normalize it and not have a cost function that gets higher and higher the more data points you have. And then this number 2 it just helps a step later on to be a little bit cleaner, but it's actually not particularly important, so don't worry about it. And if we represent what I just described, which is very intuitive, into a mathematical equation, it would look something like this. And don't let you put you off. If you don't remember this stuff, you can still get through this video. This is actually exactly what I described just now. So y hat, so the hat is this little angle on top of the y, that's the value that we predicted. So if we take that example, y hat would be the 1.5. And then y without the hat is the real value of our real data point, which would be 2 point something. So y hat minus y would be, maybe around 1 for this particular data point. So we square that. We square it because, as you can see, y hat minus y would result in a negative number, whereas if the w is too steep, so it's above the dots, y hat minus y would be a positive number. And we don't want the errors canceling each other out. We want them to just all up. It doesn't matter if it's positive or negative. A line is a line, an error is an error. So that's why we square it, to just get rid of those negative. All the errors sum up as opposed to canceling each other out. So right now we only did it for 1 point. We want to be able to repeat that for all the points. So that's what this summation is doing, taking us from the first data point, taking the error, squaring it, and then adding it to the second one, to the third one. And so we do this for all the data points, and then divide it by m, which is the total number of data points, and then divide by 2. Oh, and by the way, this j here is just a common notation for a cost function. They always use j, and this bracket wb here just means that j is a function of w and b, meaning if you think about this line, as you change w and b, you can get the loss to be higher or lower, based on how well-fitting this yellow line is. So that's all that is. So the w is shifting from where we started at 0.3 to up to, let's see here, up to 1. And you can see the cost changing here. And remember how we calculated the cost. It's just all of these lines squared, summed up, divided by the total number of dots. And look at how that changes. So if the w is too big, then the cost is high. And as the w gets closer and closer to the correct value, the cost becomes very low, 0.01. And then if the w becomes too low, then the cost starts going up again. So there's some optimal value for w where the cost is the lowest. And we've already found a pretty good value for w, but now we're asking ourselves, well, then what's the best value for the second parameter, b? So we start moving it up and down, and we can see if we move it too high up, these cost lines, or these error lines, start getting really long. And what that means is that the cost starts getting really high. And if we move it down, if it's too far down, again, the cost goes up. Where we want it is like some optimal value for b, where the cost becomes very low. Now we're going to introduce a second graph onto the screen here. What we've done here is taken the cost and plotted it against different values of w. So remember what we said just now. If the slope is too flat over here, then the cost becomes high. And then if the slope of the line is too high, the cost also becomes high. And so there's some optimal value here where the cost becomes the lowest. If we look at how this graph corresponds with this graph, if the slope goes low, like the line goes very flat, what's happening is that W is going lower and lower and lower, and the cost is going higher and higher because it's going further away from this optimal point. And then if it goes too high, then you can see that W is very high, meaning the slope of this line is very steep, and it's getting really far away from the data points again. So we want to set W to be at the best point, which is right here. And this might sound really simple, and that's really because we're working with a very limited number of dimensions. But when we talk about training neural networks, training AI models, what we're basically doing is trying to find the right value for the weights, this W, such that the cost is minimized. And remember in GPT, we're talking about, oh, this model has like 1 trillion parameters. The parameters that they're talking about is this. In this model, we have 2. And in the state-of-the-art models, we're talking about 1 trillion. At this point, those of you who still remember high school math might ask, what's the big deal about finding this minimum point? We can just use calculus and analytically work out what are the best values for W and B, and you are absolutely right. However, if you imagine that you don't just have 2 parameters, you have 1 billion parameters, and imagine that your model is not a straight line. It could be a curved surface across so many dimensions that we can't even visualize it with our human minds. At that stage, the process for finding this minimum point where the losses are the lowest becomes more of a trial and error process. So you're just trying these different values for W, different values for B, and seeing where you get the lowest cost, and then that is your model. But imagine you're trying to do that for 1 billion parameters. If you just did it randomly, you could be there for eons and not get to the optimal point of the model. So the process of gradient descent is just a more informed way of trying the right numbers such that you can get to the answer in the fastest possible way. And that's what we're going to cover in the next section. In section 2, we will be continuing with the very simple example we had from the linear regression section and explaining how gradient descent works. Gradient descent is an algorithm that we can use when training AI models to find this lowest minimum point where you have the minimum amount of losses. In other words, fitting a model to a set of data. In the next few minutes, you will learn the meaning of terms that you might have heard before, like model training, convergence, step size, and inference. Remember this cost function that we had from the previous video, and for the sake of simplicity, we're ignoring B and just working with W. As you go down the cost function, there's some optimal value of W where you can have the lowest cost. And our objective when we say fitting a model is to get to this point where we know the correct values of W such that the model is best fit for the data that we have. When you're training a model in real life, you don't know what the correct values of your W should be. So what you do is first initialize the values of all of your weights with some random numbers. So you might end up on the terrain here, this curve, in some random point. And what gradient descent is supposed to help you do is to figure out what is the most efficient way of stepping down the terrain to get to the minimum point. And of course, in this example, if you can see, oh, there's a valley to my left, you're going to just walk down to your left and you're going to find it. But imagine in an actual model training situation, you cannot see the terrain. You're standing on this massive land. You can't see where the peaks are. You can't see where the valleys are. All you can see is maybe like a 1 meter radius around your feet. What do you do? How do you know which direction to walk in to find the valley? So you might decide to take a little step to your left. Feel around the terrain. Is it heading down or is it going up? And then step to your right. Is it going up or is it going down? And in this case, when we step to the left, it went down. If we step to the right, it went up. So then you decide, I'm going to update all of my weights by taking a step to the left. and you've already reduced your cost. In this new position, you repeat the same process. Take a little step to the left, a little step to the right, and you keep going. And as you keep going, your cost will keep going down until the point where you take a step to the left, it's going up. You take a little step to the right, and it's going up. Then you know you've hit a minimum point. Now, you might ask, wait, but some models are not parabolas. Some of them might go down and then up and then down. How do you know that you're not at a local minima? So it's not the lowest point, but it is just a little valley before you get to the really deep valley. This is absolutely a real problem when you're training AI models. So what people do is to initialize the weights several times and then go through the whole process several times, and then take the lowest cost and the weights associated with the lowest cost as the definitive answer. So if you imagine, sometimes you start here and you might end up in the local minima, sometimes you start somewhere else and then you might end up in another even lower minima, then initializing it several times and running this algorithm several times will stand you a greater chance of getting to the actual lowest point. So this mountain hiking, feeling around with your feet analogy is great, but computers don't have feet. So how do they actually feel around their local terrain to understand where it's sloping and where to take that step? Well, the equivalent of taking a step with your feet is partial derivatives. And okay, this is going to look a little bit overwhelming for those of you who haven't done this for a while, but don't worry about it if you don't get everything. It doesn't really stop you from understanding what's going on. So recall, in the section 1, we had this cost function where we took the error lines, squared them, added them all up for all of the data points, and then divided it by 2 times the number of training examples. This you should completely understand. And what we're going to do here is just to substitute our equation for the line. So instead of y hat, we just replace this with wx plus b, because that was our equation for our y hat. So we put that in, and now we have, now what we want to do is to take this cost equation and to come up with the equation for calculating the slope at this point. And by taking the derivative of cost, aka j, relative to w, the weight, we can get an equation where we can calculate that slope. So the slope is the partial derivative of j with respect to w. I won't walk through the details of the calculus here, but basically if you differentiate this with respect to w, you get something like this, and then the 2's cancel out. And this is really the reason why there was a 2 here in the first place, just so it can cancel out with this and end up with a neater end result. And so now that you have an equation for calculating the slope, if you plug your w into that equation, that basically is the same as feeling around with your feet as to like where's the local slope of where you're standing. So you can see that the slope gets to a point where if that gradient is 0, then that means you've hit on the best fit w and the losses are the lowest. Let's take this step by step. We initialized at this dot. And with the work that we did just now, we now have a way of calculating what is the slope of the function at this point. And so we have this old w of 1.35, and we want to get to a new w, which has a lower, results in a lower overall cost, by taking the old w and then taking a step. And if we define the step as being the slope multiplied by alpha, we can calculate what should our new w be, and then we would take a step in that direction. Let's play that out. And alpha is what they call a hyperparameter. It is a value that you set where if you take too big of a step, you might miss your minima. If you take too small of a step, it might take you too much computational power to, or take too long to do the training. Here, we've defined the step as alpha being some value times the slope using the equation that we derived in the previous slide. We take one step, and now we have a new W. We have a new W of 1.19. And we take another step, and you can see that our old cost was 0.41, our new cost is 0.24. Take yet another step. You can see those steps are getting smaller and smaller because the slope is getting smaller and smaller. You're kind of like iterating towards this point. So you take step, 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 until your step is very close to 0. Then you kind of set some threshold and said, oh, if the step becomes so small, I'm just going to stop training and declare that we've reached convergence. And so you take the final answer for those weights as being 0.82. When you hear about Facebook with the Llama 2, they've released the weights, it just means that they've published the file where it contains all of their W's and what the numbers are, so other people don't have to spend months doing this training all over again and just use their weights as the starting point for whatever people want to do. People say that training these AI models is both a science and an art. And this is one of the reasons. This alpha hyperparameter that I talked about, let's see what happens if this alpha is too big. Then with each step, instead of stepping down and be able to reach your minimum, you might take a step like so big that you're just oscillating across that valley. Okay? So you're oscillating, and in this case, you can still reach convergence. It's just taking you a much longer time than if you set that step to the right level. But there are certain times when having those steps would actually take you just further away to just a different place. Inference is a fancy word for a very simple thing, which is you fit your model to your data, you've reached convergence with your gradient descent, and you finally set your equation to be 0.82x. And an inference is just the process of using it. So if someone came up to you and said x equals 3.5, inference means you just take 3.5, stick it in the model, and do a prediction. We can predict y should be 2.88. When you're working with GPT models, people talk about the computational power required for training versus inference. All it means is that it is the computational power required to do all the gradient descent stuff to find the values of W, and then inference is once you have all the values of W, using it to make predictions or to generate text or whatnot. In our animations, you've only seen the gradient descent process in like 2 dimensions, but if you just poke around on YouTube, you'll be able to see these really great visualizations showing you gradient descent in 3 dimensions, and of course in actual GPT models you're talking about 1 trillion dimensions, so you can't even really visualize that. But you see these little arrows is basically if you calculate the localized slope, how you take a step down to find that minimum point. And then you see the difference between this white path and this white path. They're just different algorithms that machine learning engineers have used to try and find the most efficient way for stepping down to the minimum point. So there are lots of techniques. This one's talking about momentum. It's just you see that oscillating there? That's a really cool visualization. So thank you, Diego, for making this terrific animation. In the next section, we're going to take what we've learned so far and apply it to more complex problems. In section 1, the dataset that we got actually fits on a straight line, and that was great for introducing the concepts. But in real life, most problems are non-linear. So how would we get machines to learn how to fit the right model to more complex datasets? In this video, we're going to talk about perceptrons and how a combination of perceptrons can work as a universal function approximator that can fit to any kind of data shape. Imagine if we got a data set that looked like this. If we try to fit a simple model, like a straight line to it, you can see that we're going to have a lot of errors because the data points are just going to be very far away from the model. What if we had 2 lines and combine them together? Would we be able to fit a V shape to the data set, which Of course, doesn't address all of the problems, but is already a better shape to fit this data. And the answer is no. If you add two straight lines together, no matter what the weights and the biases, you will still get a straight line. Let's just work this out. Let's say y1 is one line and y2 is another straight line. Let's say y1 is w1 times x plus b1, and then y2 is w2x plus b2. If you rearrange it, you'll see that it's just w3x plus b3. It's just another straight line. So we can't get a V shape just from adding together two straight lines. So here that's just saying if you add these two lines together, you get this aquiline, and that really doesn't help us to solve our problem. How do we fix this? We fix this by introducing what's called a non-linearity. Instead of the line being completely straight all the way, in this case it's got a kink in it. And we create this kink by just putting in this max value. If the line is above y equals 0, then we go with the line. If it's below, then we go with 0. That's what this max does. And we do the same with that other line. So we have a max, and so there's a kink here. And now when you add these two lines together, you're able to create this V shape. But of course, as we said before, V shape still doesn't fit this data set very well. It's got some out here, it's got some out here. What are we going to do about that? Well, what we can do is to keep adding these non-linear lines together, and just keep adding them until we get something that pretty much fits the shape of the data. And that's why we call it a universal function approximator, because if you add enough of them together, it can approximate any kind of shape. For a data set like this, we've given it 8 of these lines to work with, to add together to form the best fit shape. However, when we're starting out, we have no idea what would be the right values for W or B. What machine learning does is to go through that gradient descent process that we talked about in the previous section to try and derive the best values for all of these parameters such that this yellow line minimizes the losses. And of course, in the example that we gave before, there was only 1 or 2 parameters, but here we've already got 16. It'll be that much more complicated, but the underlying concept is the same. Another way of representing this line with a kink in it is with this conceptual representation called a perceptron. And so you've got X coming in, and then you add a bias to it, and then you do a max, and then you apply a weight to it, and then the output is called activation. This non-linearity is not limited to max. You can do it in any number of ways, and machine learning engineers have tried many different ways with pros and cons. So there's something called the sigmoid function, which is more of like an S shape. There's a leaky ReLU, which is instead of it going completely flat at the y equals 0, it's just got a little bit of a slope to it, etc., etc. So ours is called a ReLU, a rectilinear unit. And some people call this a neuron because it shares some similarities to how our brains work. So what we did just now to fit that complicated data set was to use a combination of 8 of these. So the X we have coming in gets fed into 8 of these with different settings for the W and the B. And then they're all summed up to form the final predicted value for Y. If you took this further and you had more complicated data with more dimensions, you can create multiple layers of these perceptrons, which starts to form the beginning of what we use today as neural networks. Although it's going to take a lot more time to dig into different neural network architectures and the type of problems that it solves, let me just give you a quick preview into the different types of architectures that the building block that you just learned can be used to build. So here on the Asimov Institute, we have a neural network zoo. There are all these different kinds of architectures with slightly different variants of the perceptron that you've learned about just now. And when they're combined in different ways, they can be used to solve different problems. For example, there's this type of model that will not just feed its activation forwards, but it is recurrent, so it feeds back on itself. And then you've got convolutional neural networks, commonly used for processing images. At this point, I can just explain the difference between deep learning and machine learning because it's really simple. Deep learning is a subset of machine learning where these networks have many layers, i.e. they're very deep. So that's all it is. What you're seeing here is still quite a lot more simple compared to the state-of-the-art GPT and transformer models. If we just take a little glimpse at that right now, here on this blog site from Nicholas Haidloff, you can see the skeleton of a GPT model. It has many different layers, each layer forms a different function, and the activation outputs of certain layers get fed back into other parts of the network. This is a good 1,000-hour course on its own right, but I hope that today's 3-part video has given you some intuition for how things work.